In this video, I'm going to work through some of the problems that we did from section 5.3 and 5.4, where we're using some understanding of the form of the right-hand side of a non-homogeneous equation to set up a guess at the particular solution. I really shouldn't call it a guess. I mean, we know it's going to work. The thing that we don't know are the coefficients of the thing, but we know the form that the solution should take. So for example, in this example 1, the right-hand side is a polynomial, and so there should be a polynomial that makes this work. And I shouldn't have to have a degree higher than second degree, as far as I can tell. And so that's what I'll start with, is say, assume I have a solution that's a second degree polynomial, and let's see if we can determine the coefficients that that polynomial would have to have. So and so this is just finding the particular solution. There is the theory about what we do with that after we find it, but this is the part that requires some practice. And this is the part that I gave you some Mathematica code for, but what I intended to do in class before the projector didn't work was to show you, how these equations come out by hand, and you can check this against the Mathematica solution. So you definitely should do them by hand a few times so that the Mathematica code makes sense. All right, so the idea here is we set up a particular solution that is a generic quadratic, and we say that if you take a generic quadratic and you take its second derivative and first derivative and add it together in combination, you should still get a second order quadratic. And so can we determine the a, b, and c that this quadratic has, so that when we plug that into the left-hand side of the differential equation, what comes out is 9t squared plus 7t plus 6. So I'm going to pause the video occasionally during this so the video doesn't get too long, but just to fill in the steps where I'm computing these derivatives. So I'm going to first calculate my first and second derivative of this. So here I have the derivative of the quadratic and then the second derivative of the quadratic, which is the constant. And now I'm going to plug those into the left-hand side of the differential equation. So I'm going to plug them in here. And again, I'll pause the video while I do that. And so even doing it by hand, you can see that I've just replaced the y double prime, y prime, and y with what they're equal to above. And as I said, every single one of those is just a linear combination of sines and cosines. And so it's not that hard to collect terms so that I have, something times the sine of 3t and something times the cosine of 3t. Every term there is some combination of sines and cosines. So I just have to go find them all. So for the sine of 3t, I'm going to have a minus 9a from here, minus 12b from here. So I'll just write these down. I won't try to do the algebra in my head, but I'll have a minus 9a, I'll have a minus 12b, and then I'll have a 5a from the last one. And then when I'm looking for all the cosine terms, I'll have a minus 9b from the yellow part, I'll have a positive 12a from the red part, and I'll have a positive 5b from the green part. And so the a and the b that I need have to satisfy this stuff. Well, I'll start here. This stuff needs to add up to 2, so that this is 2 times cosine 3t, because that's what this says over here. And I need this other stuff to add up to 0, because there are no sines in here. So this is 0 sine of 3t plus 2 cosine 3t. So I need 0 in the front of the sine of 3t and 2 in front of the cosine of 3t. And so I have 2 equations, and again, I have 2 equations of 2 unknowns. And so what you have in the mathematical file is the mathematical command to solve that, but it is just 2 equations and 2 unknowns. So, so you can do it by solving one of those equations. So like solve the first equation for A in terms of B, and then substitute that into the other equation and solve it. So that's what you would normally do. All right, so let's see some of the other ones that we had to skip past, or at least we'll see some of the other ones that I had to work too hard to show you. This is an important example because it illustrates that you don't have to create something with a zillion variables if the right-hand side is complicated. We can treat this problem as 2 separate problems. One with the t squared, because we know that that a second-degree polynomial ought to do that, and then a separate problem for the thing that has a minus e to the t, because to get just an e to the t in your on the right-hand side, a particular solution that just starts off with an e to the t will should do that. So the left-hand side one is very much like the one we just did, except you have to remember that when you don't see other terms here, that means those coefficients are 0. So t squared by itself is really a quadratic polynomial, really a second-degree polynomial, but it's t squared plus 0t plus 0. So when you plug into the left-hand side and turn the crank, the polynomial that comes out will be second degree, and you need the t squared term to have coefficient 1, you need the t term to have coefficient 0, and you need the constant term to have coefficient 0. And that will give you your 3 equations. On the right side, we haven't done one of these on this video yet, so I'll go ahead and do it. If y is at, then y prime is ae to the t, and y double prime is ae to the t. You can see this is not very interesting. When I plug that into the left-hand side, I get 9a to the e, 9a times et. And so I need that to equal -1 in order for it to match up with this guy up here. And so a should be -1/9. So the particular solution that makes the right-hand side work is -1/9 e to the t. So that'll make the green stuff, the green part, work out. So to get the red part to work out on the left, I got to do the same thing that I did a minute ago to get an a, b, and a c that will give me just a t squared on the right-hand side. And then my overall solution is just to add those 2 things together. If I add those 2 things together, then that will be a solution to this thing where the right-hand sides are added together. So in this case, we didn't do this one all the way through, so I'll just do a little bit more of it here. Our right-hand side here is a product, t e to the t. And so our particular solution is going to look like this. Some linear thing times e to the t. Again, our intuition here is that if you have something like that, then every derivative you take of it is going to still be like that. And so at the end, you're going to have something linear times e to the t that your left-hand side generates, and you want that to line up with exactly t times e to the t. And so you should be able to find out the a and the b that will do that. You can see from my derivatives that I've taken here that that's happening. When I take the first derivative, I get this, so just another linear thing times e to the t. The second derivative looks very similar. It's just a linear thing times e to the t. So it's doing what we think, that if we start off with a particular solution that's a linear equation times e to the t, then every derivative is also just a linear equation times e to the t. And so it makes sense that then the left-hand side, once I plug all that stuff in, is just going to be a linear equation times e to the t. And so I can get it to match up with the one that I have on the right that I want. So I'll go ahead and do that. Again, I'll pause here to save a little time. When I do that, you can see the four pieces again that I've generated. So my y double prime is this guy, my y prime is this guy, and my y is this guy. All of those are something times e to the t, so I know that that e to the t is going to be outside, and I just look and collect the terms. So I have at, 4at, minus 12at, it's minus 7at. Same thing with the a constant terms add up to 6, and the b constant terms add up to minus 7. So those guys all add up to, so the left-hand side becomes just this thing. Again, it's a linear equation times e to the t, as we thought. And then to get it to match up, I need this part to be 1, and I need this part to be 0. If that happens, if that first part is 1 and the second part is 0, then I will have exactly t e to the t left. And so my equations are minus 7a equals 1, and then 6a minus 7b equals 0. And I can determine that that a is minus 1/7, and then b is whatever it is, something over 49. So 6a is 7b, so I guess b is minus 6 over 49, I guess. Anyway, you can check that. But anyway, so those two numbers, I put them back into here, and that will be my particular solution to that. Notice in all of these I'm ignoring the general solution, because the general solution is going to be linear combination of that fundamental set for the homogeneous case plus this particular solution. So all that's happening in 5.3 and 5.4 are methods, which are largely algebraic, but are methods for finding the particular solutions. Okay, I think that's enough examples. I just wanted to have these on video for you to reference, because of I was not able to write as many details on the board in class as I would like to have because of the projector. So I'll leave it there, and just holler if you have questions on other problems.